In the last section on the compression unit, we'll see how to invert the Burroughs-Wheeler transform again. As we've seen, it's based on sorting the cyclic shifts, and sorting is usually a destructive operation in that you cannot unsort something if you haven't remembered what the original order was. And so it's a bit weird. How would that be possible with the Burroughs-Wheeler transform, which is based on sorting? And that's crucial. We need to be able to invert this. Otherwise, we can't decode our encoded text. So it would be utterly useless. Indeed, it turns out to be a total non-issue. You can invert the BWT. But I want to point out that this is somewhat surprising. So it's not obvious that it is invertible from the definition. And in this case, unlike in most of the other examples where we covered things like that, I want to show you the solution first and then explain afterwards why this works. My reason is the solution is so beautiful and simple that you're all able to follow the algorithm, and it doesn't really explain why it works. At least I think it's quite opaque. But the solution is so cute. So here goes. You take your the BWT is given as this array of characters. We have the assumption as before that the original string had this $ appended before it was transformed. That's crucial, so we need that. Otherwise, it's an arbitrary text, and we only get the BWT. First step is form pairs. So here's an example. That's our BWT as an input. And the $ here can be anywhere, right? For the source text, it was at the end. But in the BWT, it can now be shifted around. So that's one concrete example. And you create this array of pairs. First, the character from the BWT, and then its index. That's what's written down here. Then we sort this list of pairs. And if you were to do this in Python, it would automatically do exactly what's needed here. We sort first by the first component, and among those that have the same character there, we sort by the index in the second component. And then the last is maybe a bit less clear. So we use D as a kind of a pointered representation for a linked list and just follow pointers. Let me show this in the example, then maybe is a bit more clear. The sorting step, I guess, is clear. Also note the sorting step necessarily puts the $ in the first position because I said this is supposed to be smaller than all the other characters. So we definitely get this for free. We don't have to look for the $. And then we just take, in each step, we take this number as a pointer to where we should continue. So the first step is follow this one. At index 3, we have the next pair, A and 7. And so we produce as the first letter of the output, the A. And that's all. Now we follow through from the 7, we go down here. So follow that one. We find a B, that's what we output. And we find a new pointer. So it goes through dancing here by following these pointers. And it takes a while. But eventually, we'll find a pointer to 0. And when we've produced the $, we know it has to be over. And in this case, I mean, we started here, so we would run back into a circle. So we have to stop ourselves here. But it's obvious when we find the $, we know that we have to stop. Simple method, right? Why does that have anything to do with the BWT? Why should that be the original word? It's maybe not clear. It's true, there's a sorting step here too. Of course, I mean, there's no magic really behind this, but it just looks confusing.
Sir, not exactly the sorting, right?
Pardon?
This method is not exactly the sorting method. It's a way of rearranging it to get vectors.
Well, from here to here, that's sorting these pairs. There's nothing special going on. I mean, it doesn't do exactly what the BWT did. It's not that you take a text, apply the BWT, and apply the BWT to the BWT again, and then you get the text back. That's not how it works. Okay, it's not self-inverse or something like this. You would get some garbage if you keep applying it. Both have a sorting step involved, but it's also very asymmetric. The BWT forward, from the last section, needs to sort this matrix of strings, which is, it turns out to be cheap, but it needs a sophisticated algorithm. Whereas this sorting step here is trivial. You sort by one character. You can use something like counting sort for that. And the second component is integers, and these are also from a small range. So again, you can use counting sort. So you already know how to sort this, how to produce that column in linear time without any fancy tricks. Whereas for the other part, we'll come to the fancy tricks. So let me try to explain a little bit the connection. I mean, first of all, it's easy to follow the algorithm and compute it. So even though in big O notation, both are linear time, the inverse is much cheaper to compute. It has a smaller constant. But why does this invert the BWT? Well, first observation, we decode character by character, and we can always find the $sign because that's supposed to be unique. It's the single character, single occurrence of that thing. And we know that that comes last in the original text. So that's at least an anchor. And we can use that as a starting row. So in the BWT, we can find row in the sense of this, but also in the sense of these columns I had earlier. Okay, that's a lot of clicks back, but let me briefly show it what I mean. Rows in this sense, right? We can find the starting row by finding wherever the dollar is. So here in this example. Okay, back to where we've been. All these fancy clickimations. So we have a starting row, great. What do we do next? Well, to get the next character, we need somehow, in that row, we currently have the last character, the last column. That's where we are in the BWT. If we can find the character that corresponds to that row but is in the first column, that's what first step. Second step is find where that character in the last column is in the BWT. So let me draw it a bit schematically. We're currently in this row where we currently have this entry. That's the BWT entry. Now the first step means jump to the front of this. There's some new character A here. And then we want to find where in the BWT this A occurs. Because there's some other cyclic shift that's just one A is shifted over so that this is occurring somewhere. And we need a way to find that. If we can do these two steps, then we can jump character by character through the BWT and decode. And indeed, that is what this pointer following did in disguise. How do we do the step one? If we know the index of the column in the BWT, so if we know the how manyth character in the BWT we currently have, we know the index of the row. So we can know the index I, where we currently look at this thing here. Now the first column is all the letters in the source text, which is the same as all the letters in the BWT in sorted order. So we can just look in the sorted list, what is the ith character? No magic needed, we can just sort the characters. And the list of pairs had the characters sorted. Right? That's exactly what we did. And for the second step, we need a little observation, namely that the relative order of the same characters stays the same from left to right. So if I have several occurrences of A in the first column, like in this case, 4 A's, then the same A's must occur in the last column. It's just a permutation of the letters. And the relative order remains the same. This A is the same as this A. How do I know? Well, I know the context in the string. So this A is actually the start of A ban, and then comes $. This A is also the start of A ban, and then comes $. So the letters themselves don't have an identity, but their position in the text identifies them uniquely. So why do they preserve this order? Why is the first and second and third A, the first and second and third A on the right, in the rightmost column? That's because they're sorted by the same criterion. So the overall list of rows is sorted. So that means these occurrences of A's all gave a tie when I sorted those rows, but then I had the next columns and maybe even further columns to break the ties. The occurrences of the same characters A in the right means this A is stripped from the context, but then the rest is the same. So this ban was smaller than n. So ban is still smaller than n if I take the A away by the very same argument. That's all there is behind it. If there was a tie before for A, then what comes afterwards doesn't change order if I remove that tied character. And so that's why our pointer following method only really had to sort the first column and keep track which row things came from so that it can do this, this pointer jumping step, which effectively gives this Roman 2 step. So more concretely, like if I had this A here, these 4 A's, and I keep track of which row they came from, then I can find those rows here when I need them again. So when I have this character at the moment, I jump to the A by looking. I have the 0, 1, 2, 3, index 3 of the rows. And index 3 among the sorted characters is not just an A. I know also it's the third A among those A's. So I know where to jump to. All right. That was probably the most intricate part of the sorting thing. It's a little, you know, a bit of a mind twister maybe. But that's the climax for now. The decoding was much simpler, but both encoding and decoding take linear time in big O notation. We'll come back to what that means, suffix sorting. I mentioned it earlier. As before, or as we've seen with other compression methods, the decoding is indeed much simpler and faster also in terms of the constant factors at least. Now, what can we say about using BWT for compression? It's typically slower than the other methods we've seen in this unit, apart from this Pac8L fancy method that is way slower and trying to find more patterns still. But among the practically used methods, BWT is among the slower ones, but that's less and less of a problem. It also needs access to the entire text, which means it needs a lot of main memory to keep all the text in memory. As I mentioned earlier, initially it was dismissed as not even practical for that reason, and now it becomes a staple method because memory is just not as pressing a problem. And you get specifically from this pipeline a very good trade-off between running time and compression. It's also, the BWT also is the basis of more modern versions of this compression part. So in a way, that's the end of the pure compression evaluation here. But a second component is that the BWT is the basis of things such as the FM index, which is a way to represent the text in compressed form, but at the same time you can decompress it by asking random access questions. You can jump to any character that you want, which is, for example, not possible in a zip file. If you compress thousands and thousands of small text files and you try to get a specific one, you can open the file and Your computer will show you all the files that are contained in it, but if you open one of the files and want to see the contents, it actually has to read through the entire file. And if it's gigabytes of zip files, you'll notice. There's better ways to do this. They haven't found their way into standard compression tools because they're usually still good enough-ish. But the BWT is behind all these more modern approaches. And so that becomes more and more relevant with the topics that we'll discuss in Unit 8. And here's a quick overview of all the methods we've seen. Again, nothing new on this slide. It's just for your convenience to a summary of what we've seen. And in particular, the two new ones. We had a previous summary already. Here's another summary, adding in these text transforms. It's just an excuse to have a few more confusing acronyms on the slides.